So here's my slide, which is called Basis in Orthogonal Complement Subspaces. I'll do it by example. In fact, the yellow book doesn't have many examples in the chapter 7 on this subject. Yeah, but later on we will have more examples, especially when we start discussing with you linear transformations. So the question goes like this: find the basis in the orthogonal complement subspace like this. I hope you remember this notation. So it's all vectors. Here's the expansion for this notation. All vectors in R4 subject to this condition. That's a subspace, and that's the notation I introduced, or abbreviation I introduced for this subspace. Now the method here, well, believe it or not, it still relies on the row echelon form, but in this case it will be very easy row echelon form, because all you do, you look at this equation as an equation and you try to find the general solution to this equation. That's all you do. So if I look at this equation alone, just forget about everything else. It's the one equation with 4 unknowns, right? 4 unknowns because x3 is still present there. x3 is also there. So it's a one equation with 4 unknowns. We know how to solve that. We extract the augmented matrix. Here it is. Very simple matrix. 1 row, 4 columns. Now in this matrix, it is already in a row echelon form. Here's my pivot. These are non-leading columns, and I have to parameterize them, right? So here's my parameterization. x4 will be parameter t, x3 will be parameter s, x2 will be parameter u, and now I have 3 parameters, and I can solve for the last leading unknown, x1. I solve it from here. Here's a solution. This is a general solution to this system of one equation with 4 unknowns. System is a huge name for one equation with 4 unknowns, but still it's a system of linear equations. Now, if I convert this solution into the vector form, here's my conversion. x1, x2, x3, x4. That's my general solution as a vector in a vector form. Vector next to the t component, it has 1 coefficient in the first slot because t is here, 0 coefficient in the second slot, no t in here, 0 coefficient in the third slot, no t in here, and 1 in the fourth one because here we have t again. S parameter comes with the vector that's a typo. There's no s here. So -2 not supposed to be here. I'll fix it in a second. 0 because no s here, 1 because 1 s in here, and 0 because no s in this solution. This is a typo. It should be 0 here. U comes with the coefficients -2 from here, 1, I know what happened, 1 from the second one because u is here, 0 and 0 because no u in these 2 components. And that's the solution. I'm not sure if I can fix that type. We'll just see if I can fix that. There's a few bugs in this piece of software, and with probably manifestation. Oh no, it's not. It's good. It's 0. It's 0 here. So here's a general solution in a vector form with the t, s, and u parameters. And if you look into this representation, what do you see? You see that this is basically the span. What I'm saying is that this set, let me just call it somehow. Let me call it W, just for the abbreviation, because I don't want to copy this large symbol again. I will use W for that purpose. My W is a span of these 3 vectors. And again, it's a typo here, which I will fix momentarily. 0. It's the first time, actually, I showed you the link between these 2 classes of subspaces. Remember, before, every time we look at a subspace, it went either the one way, either it's orthogonal complement subspace, or the other way, it's a span subspace. It's the first time I showed you that actually we can link these 2 via finding general solution. Doing the link the other way, when I say other way, converting a span subspace into the orthogonal complement subspace, I think it's also doable, but I think it's a little bit harder than this way. Anyway, now we know the basis. Here's the basis because these are linearly independent vectors, right? If you form a matrix out of them, there will be pivot, pivot, and pivot. Everyone will be a leading column. So this is a basis for my span or for my orthogonal complement subspace, and we have 3 elements there. So the dimension of this subspace is 3. Dimension of this orthogonal complement subspace is 3. Any questions?